Record, and here we go. All right, so we're going to be working through this exam 3, one of the practice exams that's posted, and I'll do maybe not everything, but I'll touch on a couple of the different types of problems in here. So most of the exam is going to be about series. That's where we spent most of our time, but we'll also be looking at, as this first problem says, some problems that are just about sequences themselves. And so with sequences, if they're given in these closed formulas, then this is not any convergence tests. It's taking a limit or trying to treat it like we did horizontal asymptotes. So in this case, B here, the long way I would say is we can use L'Hopital's rule. But when it's rational functions, there is a shorter way, and that is look at the biggest terms around. So both of these have n squareds. And when that's the case, a rational function where the powers match, we can take the coefficients in front of them. So B is -4. The 4 on the top divided by the -1 on the bottom. And if you're going to use this kind of shortcut, a little bit of explanation of what's going on, that -4 arises since they have the same powers. Okay. C is one where we really will need to use L'Hopital's rule. And the first move, and this I would say in most cases, having the negative exponent just makes things kind of harder to understand for taking limits. And when things appear in series, it's often easier to write it with a fraction rather than the negative exponent. And especially here, this is the case because now we can use L'Hopital's rule. These are both going to infinity. And so if we differentiate them, the derivative of the natural log is 1 over n, e to the n is just e to the n. And then what happens in this case is instead of a fraction on the top, we can move that bottom of the fraction into the bottom of the larger fraction. And then this limit we can find, the top is fixed and the bottom is going to infinity. So this limit is 0. And then with A, there are a lot of sequence specific things going on here. So that's why I saved this one for last. When we're looking at this limit, one thing that we had seen with alternating sequences is if we look at the non-alternating part, if this sequence goes to 0, it still goes to 0 when it's alternating. It's bouncing around, but bouncing closer and closer to 0. If this converges to like 1 or something anything other than 0, then it's bouncing between positive that value and negative that value when you put the alternating factor back in, and then that alternating sequence will diverge. So we need to understand what this is doing. And the factorial rules out L'Hopital's rule. This is not something we can differentiate, so we can't use L'Hopital's rule. However, factorials, n factorial looks like n minus, or I'll put it like this, n factorial is n times n minus 1 factorial. Because n factorial is n minus 1, n minus 2 multiplied down to 2 and 1. But these terms starting at n minus 1, that is n minus 1 factorial. And then we're left with, there's an extra n at the beginning. So in this case, we get this simplification like we've often been seeing in the ratio test, except we don't get everything canceling. We do get one factor canceling. And so even though we're starting at a lower value, factorials do grow to infinity. As you keep increasing n, you are multiplying more and more things together, so that's going to infinity. And then since the top is fixed, the bottom is increasing, that limit is 0. And since that limit is 0, that means if we put the alternating piece back on, that limit is also 0. Okay. Questions about any of these parts? It's kind of a blur now that we're done, trying to fit it into this space. But any questions about finding these limits of sequences? How much work do you need to show? I would say the work here is what you would need to do. There's really not anything, well, this red stuff you don't have to show. That's just kind of explaining the simplification. But I would say this is pretty representative. B, an alternate work would be actually showing L'Hopital's rule. But I guess steps like here, finding this limit, this is a kind of limit that we've done in a bunch of different settings, so we can just say that that's true. But I'd say this is about the right amount of work for these problems. Okay. All right. So then let me clear this off. Let's look at the next one. Okay, so it's a little more white space here. Okay. So number 2, show these series converge and find their sum. One thing in here where it's saying to actually find the sum, that didn't work the way I wanted it to. When you're asked to find the sum, there are very few cases where we can actually find the sum. And actually they both show up here. This first one is telescoping. If we imagine this square root going over the whole thing. And the second one is geometric. And those are the two types of series where not only can we tell that if they converge, but we can actually find the sum. So for B, with geometric series, a place there might be some work is putting it in this form. So we've seen a couple instances where we need to use maybe some exponent rules or some algebra to put it in this a times r to the n form. But once it's here, there's not really work to do. There's observe in this case. Since the r 3/5 is less than 1, then the geometric series converges. And then what it converges to, this is where, and actually one of the few places where this happens is we need to look at where are we starting. So since we're starting at n equals 2, when we find this formula, the bottom is always 1 minus r. This is always the same, no matter where we start. But on the top of this sum is that starting value, put that in for the exponent, and that's the numerator in this formula for the sum. So on the top, it is 4 times 3/5 squared. And for the sake of time, I'm going to skip over this, but I'd say try to simplify this a little bit. Either put in your calculator or you can simplify the fraction. Right, but this is the sum for this geometric series. The formula you might have in your head is a over 1 minus r, but that is the sum of geometric series if you're starting at 0. Because if n is 0, r to the 0 is 1, and you only have that a. If you're starting somewhere else, you have some of the powers too. Okay. Questions about that one? And if you have questions, feel free to stop me either unmuting or dropping something in the chat as we're going through these problems. With a here, if we're finding the sum and it's clearly not geometric, then what you can expect is for it to be telescoping. That's the other way of finding these series or the sums of these series. And what we can see that says, yep, telescoping is the right way to go, is that we have basically the same expression. It's just offset by 1 a little bit. Is that right? Okay. Maybe there wasn't a typo. It looked kind of strange, but I think this is actually right. Unless something goes wrong, I'm going to try to find it. Yeah, so I think this is right because we have an n and a n plus 1, and those are offs. It's the same thing, a square root and then a plus 1, but it's offset a little bit. So when it's telescoping, this starts by actually writing out what do these partial sums look like. And so S1, and here, this is another place you want to check. We're starting at 1, so that's the first number that we use here. If we put in 1, and this first one is just the first term, this is 1 over the square root of 1 plus 1 minus 1 over the square root of 2 plus 1. And nothing happens in the first case, but if we go and add up the first 2 terms, we always get what we had before, but there's going to be something added on the end. So 1 over the square root of 1 plus 1 minus 1 over the square root of 2 plus 1. And then we put 2 in for these ends, and we get 1 over the square root of 2 plus 1 minus 1 over the square root of 3. If we put 2 in, we get a 3 under the square root this time, plus 1. And if we get S3, this means add up the first 3 terms, and we'll do 1 over the square root of 1 plus 1 minus 1 over the square root of 2 plus 1. Write smaller to try to squeeze this in. 1 over the square root of 2 plus 1 minus 1 over the square root of 3 plus 1. And then if we put in 3, now we get another 3 in here, but it's positive this time. And then if we put in 3 to the n plus 1, we have negative 1 over the square root of 4 minus 1. And if telescoping is going to work, and what we see actually happening here is some cancellation happens. There is something at the beginning that never gets canceled. There's something on the end which hasn't been canceled yet, but will in subsequent partial sums. But then there are the things in the middle that do cancel. So these terms with the square root of 2, they are exactly the same, except this one is negative. So those add up to be 0. And then we have the square root of 2 terms that add up to be 0. And then the square root of 3 terms, and those also add up to be 0. So then the question is, if we say this pattern continues and we want to jump into the middle somewhere, then we need to think what never cancels at the beginning. And here we can go ahead and simplify this. The square root of 1 is 1. 1 plus 1 on the bottom is 2. So there's always this 1/2 that's at the beginning. But then at the end, there is 1 over the square root of n plus 1 plus 1. When S1, we have a 2. In S2, there's a 3. It's 3. There's a 4. If we have n, it's the next number, n plus 1. And then given this, we use what is the actual definition of sums of series. The sum equals the limit of these SNs. And what is special about telescoping is this is, in general, the sum is the limit of these partial sums, but now we have an explicit formula. And if we take this limit, although 1/2 doesn't have any n's, so it's stuck, but now this square root, that's going to infinity, plus 1 helps, but that means that our fraction that we're subtracting, the top is 1, the bottom is going to infinity. So this subtraction gets smaller and smaller, and its limit is 0. So this limit, which is the sum of this series, is actually 1/2. Questions about either of these problems?
So for the telescoping series, it's not always gonna look like that, right? It's kind of already written out in kind of an expanded form.
So do you mean it won't look like this is something minus something else?
Yeah.
Maybe. The one kind of special case where you can find this is if it was a partial fractions problem. And so that would be like if you wanted to find the sum of 1 over n plus 1 times n plus 3, something like this. Then the step would be finding the partial fraction decomposition. It would look like, you'd have to do this, a times n plus 1 minus, I think, b over n plus 3. And so in this case, there's a little work that could happen beforehand. But for things like square roots, that wouldn't really work with partial fractions. And so in this case, it kind of has to be presented like this. And what I would say the giveaway, or what you can kind of word that you can hone in on, is when it asks you to find the sum, it's either geometric or telescoping. So even if you're given something like this, which isn't presented ready to be telescoped, being asked to find the sum says this has to be telescoping, and for rational functions, the way to fit it into that telescoping kind of appearance is to do this partial fractions.
Okay, thank you.
All right, so let's move on. Okay. So number 3 here, and can I get rid of my sidebar? Nice. All right. So number 3 is saying, first, check the test for divergence. This won't always be there, but it's a good first test to try, really, no matter what. In this case, it's saying, let me know if the test for divergence works or not. And if it doesn't work, do something else. So the one of these where the test for divergence will work is actually B. And the test for divergence says take the limit of just the sequence. So we have a bunch of other tests that say, like the limit comparison test, the ratio test, and root test, you take a limit of something, but the test for divergence is just take a limit of the terms of this series. Don't do anything to it. And in this case, if we use L'Hopital's rule, then the exponentials just stick around, but the 1, since it's constant, that's derivative is 0. And without the 1, we can cancel the e to the n's, divide that by itself, and we're left with just -1/3. And that is, well, it's a constant, so with the limit is that constant value. So in this case, we find the limit of the terms of the series, or we find the limit of the terms of the sequence used to create this series, to use that terminology correctly. And what we notice is this is not equal to 0. So the series diverges by the test for divergence. Nope, not A. So A, in this case, this is saying, try the test for divergence and see what happens. And in this case, you can either use L'Hopital's rule again. In this case, because we have powers of n, we can do it a little faster, and we can say this limit is 0 because the bottom power is bigger. The bottom is 11/4 and the top is n to the 1st power. So in this case, since the limit is 0, the test for divergence doesn't apply. So we'll have to use something else. And since that something else is going to take up a little bit of space, I'm going to clear this off. But questions quickly about, or not quickly, but before we move on, questions about using the test for divergence here. So then what about A? So first question is, what test should we use? And so we have this list that we can run down, and we just checked it's not the test for divergence, it's not a p-series or geometric, but speaking of p-series, it pretty much looks like one. If there's only powers of n around, that is close enough to a p-series that we can compare it to a p-series. And the way that we pick the comparison series is identify the biggest powers on the top and bottom. In here, that's not such a big deal. There's a 1 there, and then there's 11/4. And so we'll compare this to the series that has an n and an n to the 11/4 on the bottom. And then we can subtract these exponents. So the top has 4/4, the bottom has 11/4. If we end up canceling, we have 7/4 more n's on the bottom than on the top. Okay. Questions about picking this comparison for the comparison test?
How did you get from 11/4 to 7/4?
So here you can subtract the exponents. So the new exponent is the 1 on the top minus 11/4, and that's -7/4. And then I put that on the bottom of the fraction.
Got it. Thank you.
Other questions? Okay. And before moving on, I said something about pick the biggest power. Even if there was other stuff around, like if this even had, let's say, a plus the square root of n and then plus an n squared on the bottom, well, the 1 is still the biggest power because this is n to the 1/2. And in this case, 11/4 is the big power because that's 2 3/4, and this is just a 2. So even if there's stuff around, pick the biggest power from the top and the bottom and use those to make a fraction. Since they'll just be powers of n, you can combine them into a single power in the denominator, and that'll be a p-series. So having picked this, there are two things that we need to do. First is we need to say that this comparison p-series, what does it do? And in this case, it converges, yeah. So converges since the power is bigger than 1. You can slip in the p-test. Yeah, geometric series and p-series are simple enough that if you don't mention the test, it's not a huge deal. And if this helps, great. If not, then don't worry about it. But the way I remember which way the p-test goes is I know that 1 is the dividing line. I know that 1 diverges because that's just the harmonic series, but I remember at 1/n squared, that converges. And so the other side, if you're smaller than 1, that's the side that diverges, is the mental gymnastics that I do to remember which side is converging. Okay. So then what we do is, in this case, we'll do a limit comparison. You could set this up for a direct comparison. Especially for p-series, is just a little harder for me to deal with because you have to have the inequality going the right way, and sometimes it doesn't quite work out. But the limit comparison test is more flexible. So here, the limit comparison test says, take the limit of the series you started with, n over n to the 11/4 plus 5 over 1 over n to the 7/4. And then instead of dividing by a fraction, flip the denominator and multiply. And what we'll see happening, you can expect to always happen, at least kind of in a high level way. So flipping this fraction, we get n to the 7/4 on the top, 1 on the bottom. And then if you multiply it across, you add the exponents together. So there's 4/4 plus 7/4, we get 11/4. And what you should expect to happen is you want those powers to be the same. Because if they're the same, then the limit that you get, there's a horizontal asymptote that's not 0. So this equals 1. One thing to point out here is that if you divided these in a different order, that wouldn't affect the way the test works. It might change this number, but if this number is not 0, if you take its reciprocal, that's also not 0. So you don't have to worry about which one is on the top, which one is on the bottom. So then the last step is we need to decide, what do we actually say as our final conclusion? And in this case, since we get something that isn't 0, but is a finite number, we don't use this on its own to say converge or diverge, like some of the other tests, especially the ratio and root test. What this means is, okay, whatever your answer to part 1 was, and it was converges in this case, that's your answer for what you started with. So our last point is by the limit comparison test, for emphasis, we'll say the original series converges to, with this extra emphasis of there are 2 series around. We made up this comparison series, but we want to go back to the very first series that we started with. Questions about this part, this use of the limit comparison test? Okay. And right, I'd say besides actually executing the limit, the 2 things to make sure that you're comfortable with are finding the comparison is always the biggest powers around. And since you're just taking powers, that'll give you a p-series, and that's easy to tell if it converges. And then what you should expect to happen, and if it doesn't happen, then something went wrong, is in this limit, you should have the same powers appearing. because this 7/4 is exactly the number that if you multiply it by n, it gets you up to the 11/4. So let's see what else we've got. All right. So for 4 to make sure we hit a couple of these other types of problems, are there any of these 4 that you'd especially like to see? I can go through and kind of quickly say, this one use this test, this one use this test, but are there any that you'd really like to see worked out? Or maybe I can say what test we would use, and then after that, you can let me know if there's one you'd like to see. Okay, so let me kind of do a quick rundown of what are the tests to use and what about them makes that the right test to use. So in A, the big thing that sticks out. Okay. So all right, so we'll run through kind of quickly, but then we can pick out those couple specific ones. Okay. So in A, the big thing that sticks out is you have nth powers. And if everything around is an nth power, that suggests the root test. The root test is also good because it does say converging absolutely or diverging. So it does have something to say about this kind of question. In B, we have a factorial, and that on its own really says probably the ratio test, unless there's some good reason not to. And that good reason might be you try and it doesn't work somehow. But that's the first thing that jumps into your head, that factorial, and that there's multiplication around. So that says the ratio test. In C, the thing that we can look at is the term looks like, or the terms of the series look like the alternating part and a positive part. And this is a good candidate for the alternating series test, especially because the positive part is 1 over an increasing function. And that means it's really quick to tell if it fits into the alternating series test framework. D also has an alternating part, but then we would want to think about this as the positive part. And in this case, looking ahead to what happens, and I can go through it in more detail if anyone would like, but in this case, this one will actually diverge by the test for divergence. Really quickly, because here the positive part goes to 4/5. The powers are the same, so we take the ratio of the coefficients there. And we'll really quickly write this out. This limit is 4/5. And if you put the alternating part on something that doesn't converge to 0, like we have in this case, that limit doesn't exist. And since the sequence diverges, the series is going to diverge too. So this is a really quick rundown just to identify what tests we would use. Questions about picking the test. And there was a request to work through A and B. Okay, so let me clear this out. So A, because it's so perfectly set up for the root test, this one can go pretty quickly as long as you know what the root test is and what conclusion you need to make based on the limit that we get. So for A here, we want to take the limit, and the root test says take the nth root of the absolute value of A to the n, where A to the n is the sequence in here. Taking the absolute value, what it will do is get rid of the alternating part. If you like, you can look at this as the alternating part and then n to the n and then 4 to the n. You can break up the bottom into the negative and the 4. So in this limit, we're taking the nth root of n to the n and 4 to the n. And because we have those nth powers, the nth root is exactly the thing to cancel those out. So we get at just n over 4, and the n goes to infinity, the 4 doesn't stop it, so we get infinity. And then we need to think, what does this mean for the series? So what does this mean about the series according to the root test?
That it diverges.
Right. So the root test and the ratio test, their decision point is you find this limit bigger than 1, you diverge, less than 1, you converge, 1, you need to do something else. So in this case, the series diverges by the root test. And even though this problem 4 has these 3 different pieces, once we find it diverges, that's all. Like we don't have to worry about like an alternating series test or anything. This answers the question. So then B is a case where we want to use the ratio test because we have the factorial in particular, and the other pieces, the exponential and the polynomial, those work in the ratio test too. So the ratio test is absolute value of an plus 1 over an. In this case, the absolute value doesn't do anything, so we can just forget about that. And so what we need is on the bottom is just the terms as it's written, n, 2 to the n, and minus 1 factorial. On the top, we increase, or we put n plus 1s in where all of the n's are. So instead of just an n first, that is n plus 1, 2 to the n plus 1, and then actually n factorial. Adding 1 to the n undoes the subtraction that's in here and gets us back to just n. Then what I'll do in kind of a bunch of steps at once, what always happens is we flip the bottom and multiply, and then we group the pieces according to which part of the formula for the terms of the sequence do they come from. So we get the n plus 1 divided by n, we get the 2n plus 1 over 2 to the n, and then n minus 1 factorial over n factorial. So these pieces from the top are in the position they were in before, n plus 1 and 2n plus 2 to the n plus 1 were on the top, n factorial was on the bottom, but then we have their corresponding pieces from the denominator get flipped, and now these were on the top, now they're on the bottom, and the factorial was on the bottom here, and now it's on the top. So then we can get some cancellation. The polynomial part, there we don't actually get cancellation. It'll go away in the limit, but we don't get the same kind of cancellation we do for powers and factorials. So this part we'll leave alone. Here we get an extra 2 on the top, and the bottom has an extra factor of n. And if you need to write out the factorials, do it. But if we see more and more of these, you could potentially be comfortable saying, I know what's going to happen. The bottom has an extra n and everything else cancels. So let me just jump there. And then we actually take the limit. And in this case, two ways to think about it are that this polynomial part, this is going to go to 1. And the polynomial parts will always go to 1 because you end up with the same powers and the same coefficients, just maybe slightly different polynomials. And then 2 to the n, that goes to 0 because the top is fixed, the bottom's going infinite. And so this limit is 0. You could also multiply the denominators together and then see the bottom has n squared while the top just has an n. So that means that will also indicate the limit goes to 0. And then we have the decision point. We got 0. 0 is good in this case, in contrast to the limit comparison test, where that means we didn't have a good comparison. But in this case, we can say this 0, the thing we're really looking at is that it's less than 1. So by the ratio test, the series converges absolutely. And the ratio test does give absolute convergence, which again means even if sometimes we have to check two things, if you just diverge or you just know you converge absolutely, you're done. You don't have to do any more. Questions about these ones? So then let me see what else we want to do. Real quick hits. This one, you can check, diverges by the root test. This one, either two ways, this converges by the root test, or what we shouldn't forget is that this is actually a geometric series test. And about B, let me just say, the way you would go about doing this one, and this, I'm going to be really brief because this kind of showed up in the extra alternating series test video, but is not going to be on the exam because it only briefly showed up and we didn't really give it the time that it takes. In this case, what you would want to do is put absolute values on. And you can check that this converges absolutely with some comparison tests. And for the sake of time, and there was an example in the video, but it's not going to be on any tests. So we'll just kind of pass over it. Okay. And so I think as a last thing to do, we can talk about number 6 and these two different tests. Or one thing we didn't really do is C. This one will actually be conditional convergence. So are there preferences about which of those two sequences or two series you'd like to end with? Okay. So let's talk about this one. Right. So super brief with this one, alternating series test. And I'll just write this before spending our time with the other one. In this case, you look at the non-alternating part. This decreases and the limit is 0. So this converges by the alternating series test. But then if you look at the non-alternating version, this diverges by a comparison test. What I would do, although there are other ways of doing this, would be limit comparison with the series 1 over n, because that's the biggest power on the bottom. Okay, so that's the super quick version of how to deal with number 4 for C. Right. So let's come down here. So the first part, or let's do this one way, the limit comparison test. And here, this throws a wrench into our pick the big part of what's happening. And what works as a comparison, or the simplest comparison to make, would be compare this to the series 1 over n squared. Why you would want to pick this is, well, it's easy to tell it converges. The P series and P is 2, which is greater than 1. So this converges. But why you could look at this and say, let me only take the n squared instead of the arctangent, is because arctangent has this asymptote at pi over 2. So compared to n squared, it's not even going to infinity. Like when we had that example above that was like we picked n and n to the 11/4 or something like this. In this case, we take both because, well, they're at least both going to infinity. This one just turns out to be bigger. In this case, arctangent of n levels off So if we just don't even use it, we're going to be able to, we'll see when we take the limit, we'll be able to make this work. Okay. So what does it look like if we try to make this work? So this converges. If we take the limit of arctangent n over n squared plus 1 divided by 1 over n squared, then flip and multiply, so we get n squared times arctangent of n over n squared plus 1. But really the way to separate it is have n squared over n squared plus 1 and then arctangent. The reason for this separation is that this limit is, because it's the same power as the limit comparison test should have happen, that goes to 1. And arctangent, it has an asymptote at pi over 2. So we don't really need to worry about arctangent because it levels off to some number on its own. So this is pi over 2. And then we can say the fact that this is greater than 1, that doesn't matter. All that matters is that this is a finite number. So by the limit comparison test, we'll be more specific. The original series converges to. Questions about this one? So the arctangent in here, I'd say why this works out kind of nicely is because this is an inverse trig function, but what we're really using is it has this horizontal asymptote. Okay. And as the last part, so for the integral test, I'll leave as kind of a check that if it doesn't happen, it's not the main thrust of the problem, but this is positive, continuous, and the hard one is decreasing. So there, it's not clear that this is, so it's not 1 over an increasing function. So you'd have to check the derivative is less than 0. But the main part is this actually is a function that we can integrate. Because if we integrate arctangent of x over x squared plus 1, if u is, so the u substitution that works here is u is arctangent, and the derivative of arctangent is 1 over 1 plus x squared. So there's a reason why these pieces are in here, and since it's saying use the integral test, somehow the integral has to be doable. And the way that it works is that we actually have this u substitution that works. So then this is integrating just u, which is u squared over 2. And for a second, this looks like, whoa, u squared goes to infinity. That means the integral is going to infinity, which means this diverges. But why this turns out okay is it's not really u, it's not the variable itself, that's actually arctangent in there. So arctangent of x squared over 2. And since arctangent has an asymptote, this will have an asymptote too. So then we can carry out the improper integral. Arctangent of x over x squared plus 1. Putting a couple steps in here. We're going to take a limit, but then we know we're integrating, and that means we are evaluating the integral from 1 up to t. Then we put these in. The t just changes the variable. And this turns out, we need to do a little bit of trig. This is pi over 2. And arctangent of 1 is pi over 4. Which you can simplify a bit to get what fraction of pi it is. But the main takeaway is that since the integral converges, try to squeeze this in here by the integral test, the series converges to. Not to whatever number this is, but it does converge. Okay. All right. So that's the last problem we'll be able to do. We did most of them, so that's pretty good. Any kind of last quick questions? All right. So this video is going to be posted, and I can. And there are some other practice materials up. Some of them. So this one, it looks like this because this was March 2020. It had to be a take-home exam because we weren't at school. It'll look like the other exams. So it'll look like the practice exam, the other practice exam that's posted, and it'll be a lot like the other exams we've had in class. This one is formatted differently for kind of reasons we all remember. Okay, all right. Then I'll close this off, and this will be posted in a bit, and I'll see